Okay, so here we go. 6.5 number, or 6.5a, number 15. All right, so again, as I said yesterday, what all of these problems have in common is that there's some sort of non-conservative force, okay? So a force other than gravity or, elastic spring or something like that. You've always got a non-conservative force doing work, and that work will serve to change the total energy of the object, okay? So every single problem, somewhere in the middle of the problem, you're going to use these two equations, okay? And the idea is you'll use one of the equations to find the work, and then once you've found that work, you plug it into the other equation to find some missing thing. Okay? I'm not ignoring you, LaShawn. Let me say one other quick thing, and then I gotcha. When I do these problems, I start every one the exact same way. Okay? I start by identifying the important points in the object's motion. Okay? And at each of those points that are important, I ask myself, what do I know about the energy? Do I know the velocity, so I can find the kinetic energy? Do I know the height, so I can find the GPE, the gravitational potential energy? And if so, I find all that. So I really try as much as I can to complete this equation. Okay? And if I get there, great. If not, then that's when you got to look at this guy. Okay? So I'll sort of model that as we go through this problem. Okay? But before I do, LaShawn, you got a question? Talk to me. What do you got? Did I?
Yeah.
Oh, cool. All right, so number 15, half the battle in 15 was just figuring out what was going on for that. Oh, and, right, thank you. If you didn't notice, in the back is where I leave my handout, so there's a paper copy of the worksheet back there if you want to grab it. Sorry, not to single you out. So, where's my copy of it is the big question. Boop, boop, boop. Oh, right in front of me. Okay, so half the battle is just figuring out what's going on. So it says a 4.5 kilogram ball is dropped from a height of 5 meters. So 4.5 kilograms is like 10 pounds, so it's a pretty heavy ball. It's being dropped from high up. It says you reach your hand in to try to catch it when it's 2 meters off of the ground, and your hand moves down 0.5 meters as you catch the ball. So if you need a visual, it's this. The ball's way up high in the air. It falls, and then you catch it. And as it hits your hand, boom, it pushes your hand down, right? Right? Newton's third law. If you're going to stop the ball, you've got to push the ball up. And so, the ball pushes your hand down and your hand moves down, right? So the 0.5 meters is how far your hand moves between you making contact with the ball and it stopping. Follow? All right, so as always, problem solving, you want to start by identifying the important points, make a drawing of the path that it's following. So here we go. Here's the ball. It begins at a height of 5 meters. We're going to drop it. When it gets to a point where it's at a height of 2 meters, you're going to try to stop it. And then you finally succeed in stopping it after it falls another 0.5 meters. So what should I call my height here, you guys? 0.5? No. 1.5, right? Because it's going to go down another half a meter from that point. Everybody good? All right, so before I go any further, does everybody understand kind of what these 3 points represent and why I zeroed in on those 3 points? Okay, so let's give them names. I'm going to start using Roman numerals instead of letters. So we'll call that point 1, we'll call this point 2, we'll call this point 3. That way we won't get confused with the parts of the problem. Okay, height is important because if I'm trying to find total energy, the height will allow me to find the GPE, right? Just do mgh, right? Mass times 9.8 times the height. So let's take a quick second to do that. So this GPE, if you figure it out, ends up giving you 220.5 joules. Everybody good up to there? This one, GPE, ends up being 88.2 joules. And down here at the bottom, the GPE ends up being 66.15 joules. So that was just, I did MGH 3 times for each of the different heights. Everybody good? Sure. think about, you guys? Kinetic energy, right? And so to think about the kinetic energy, we need to think about velocity. Cool? All right, so let's think about the velocity. What's the velocity up here at point 1, you guys? 0. It's being dropped from rest. Oh, that's cool. That means that the kinetic energy up there is also going to be 0, right? Aha! That means I can find the total energy up here. It's just going to be 220.5 joules. Any problems up to there? All right, down here at part point 2. So the idea is the ball has already fallen, down to a height of 2 meters. It's moving now, so it's got some velocity. Is it 0 because I'm stopping it? No, it hasn't gotten to 0 yet, right? This is the point where I'm just reaching my hand in there to try to stop it, right? So what's the velocity? We don't know. All right, well that means we don't know the kinetic energy. And since I don't know the kinetic energy, I also don't know the total energy. Everybody good? All right. How about this last point? Let's see, down here, do I know the velocity here? What do you got, LaShawn? 0, right? Because you've stopped it. That's why that point was important. That's the point where you stop the ball, right? All right, cool. Well, that means that my kinetic energy here is going to be 0, which means that my total energy is 66.15 joules. That's a J. Questions? Everybody's good? All right, so I did all of this. I shouldn't say that. So, no, I'm totally getting out of myself. Okay, so the question wants to know how much work Roy did, right? Or is it Roy, I assume? You, whoever is catching the ball. It wants to know how much work that person did stopping the ball, right? So there are 2 ways of finding work. You can basically do force times displacement, right? Why don't I need to worry about the angle? 180. Yeah, it's 180, right? The ball's moving down, we're pushing it up, right? Okay, but even so, I still can't use this equation yet. Why not? Yeah, we don't know, what is our non-conservative force? Like, name the non-conservative force. Gravity's conservative. The hand pushing up, right? Everybody okay with that? I'm getting more blank stares than I hoped they would. Are we good with that? Okay? So, but the problem is, I don't know the force of the hand. I don't know Roy's force. Okay? So this equation's not going to help me any, so I got to use this. All right? So my question that I should be asking at this point, because I'm kind of stuck, I'm sort of at a pause in my train of thought, is what do I know about the total energy? What do we know about the total energy? So stop and think about that. So Lucy, you want to get me started?
From point 1 to 2, the force acting on it is gravity, which is conservative. So you know the total energy at point 2 is going to be the same as point 1.
That was perfect. Ooh, crayon. I've never used crayon before. No, that's not going to work, is it? All right, sorry. This is not the time maybe for me to experiment with pens. Sorry. Okay, so yes, I agree with you. So Lucy just said between point 1 and point 2, the only force on it is gravity, right? That's a conservative force, right? So what should be true about the total energy between those 2 points? Should stay constant, right? Does that make sense, you guys, or no? Because the only thing that's happening between here and here is you're converting GPE to KE, right? But our total is constant. Sorry. Cool? All right. How about between points 2 and 3? Is my total energy there constant? No. How come? Because there's a non-conservative force, right? There's work done by Roy or whoever. That's an R. My smartboard has been particularly ornery today. Okay, everybody good? All right, so based on that train of thought, my total energy between here and here is constant. My total energy between here and here changes. I can fill in some more information over there. What do we know, you guys? What does the total energy here have to be? Same as it was up here, right? Okay? And so now, if I wanted to, I could find this kinetic energy by just subtracting. And I could find this velocity once I know the kinetic energy, right? Follow or no? All right, so you can do that. The problem doesn't ask us to, but just as a side note, it's a thing we can do. Cool? All right, we've done all of the hard parts. Are there any questions about what we've done here? All right, so now question A says, how much work did Roy do? Well, the work done by Roy is, he's our non-conservative force, right? So that's our change in total energy. So that's total energy final minus total energy initial. Now, here's the big thing that I want to make sure you guys understand. What's my final point and what's my initial point for this problem? The final point is point 3, because that's the point at which Roy stops doing work. What's the initial point? 2, right? Because that's when he begins exerting force on it, right? There's no work done between here and here. Well, no work by Roy. All of Roy's work is done between 2 and 3. Follow? Questions, you guys? All right, so what are we going to get? The total energy at point 3 is 66.15. Total energy at point 2 is 220.5. Subtract this and you get negative, is it 157.35? Is that right? I did that in my head, so. 154, sorry. Thank you. Where did I get 7? Okay, everybody good? All right, so that's how much work Roy did, right? Because that's how much he changed the total energy by. It went from 220 down to 66. All right, my 5th hour got derailed because there were a couple students that were like, well, why don't we just use points 1 and 3? And mathematically, it's the same thing, right? But why am I calling attention to the fact that we really want to do points 2 and 3? There's two reasons, one mathematical and one just conceptual. So conceptually, why am I calling attention to that? What's the point? It's the work done by non-conservative forces, and that only occurs between which 2 points, you guys? Between 2 and 3, all right? Maybe the more convincing argument is this. So what this represents is the work of Roy. Question B wants to know what's the force of Roy. All right? So check it out, you guys. Force is not energy. Force is not work. They're not the same thing. All right? Force is how hard you're pushing the object. Okay? So the thing that equates those, or the thing that allows us to, I'm going to say convert. I'm not happy with the word, but there's not a better one. The thing that allows us to convert from work to force, or vice versa, is this top equation. We just found the work of Roy. I know my displacement, so I can find the force of Roy. Make sense? All right, so last step then. This stupid smartboard is being... Insert bad word. It's like I can make it giant or small. I don't know. I'm having a bad smartboard day. All right, so here we go. So work of Roy is force of Roy times displacement. I'm not going to worry about my angle because it's either 0 or 90 or 180. So you get negative 154.35 equals the force of Roy times, what was our displacement? Point 0.5, right? Because that's how far it moves as it goes from point 2 to point 3, right? Do you guys understand why it's just the displacement from 2 to 3? Okay, so that's the big deal. Because if you use 1 and 3, then your displacement's 3.5 instead of just 0.5. Okay? And so the force of Roy ends up being 308.7. My happy face is wearing a bow tie today. Cool, you guys? Yeah, push on. What's up?
Do you not care about negative?
So I guess if you wanted to do this accurately, probably the best way to do it would be to think this displacement, technically speaking, is negative. So if you make this negative, then the negatives cancel and you get a positive force. It's probably the best way to go about it. Okay. I'm really unhappy with the way I taught work this year. I changed from the way that I usually do it, thinking it would make it easier, and it totally did. So next time I'm going to go back to the way I usually do it. Do you understand that the force needs to be up? Sure. So then it's got to be positive, right? So I think I'm going to go with that, because otherwise I got to go back and reteach some stuff about the way I did work. I didn't do anything wrong, but I made it more complicated than I should have, I think. So, yeah.
So work is whatever opposes it is that direction. So that's right. Positive.
Right.
And force is like its force direction.
Say that again?
So force stays on direction.
Yes, correct. Yeah, I gotcha. Yes. So if the force is opposing the motion, then one of these two vectors has to be negative, right? You know, either one of these is pointing in a negative direction, whether it's your displacement or your force, doesn't matter. Something in there has to be negative, and that then results in a negative amount of work. Cool.
Yeah.
Okay. All right. Are we good with this? All right, and then part C is basically the same thing, except instead of 0.5 meters, it's 0.1 meters. So you go back and you do the calculations again. Would you guess that the force is bigger or smaller in those circumstances? Bigger, right? Because you've got less distance over which to stop the object, right? Cool? All righty, that is number 15. Are there questions? Okay, cool. All right, so let me do this.